Thanks, Fidel. As I mentioned to you on Monday, we did have a last-minute change to the agenda. As you may remember, early we advertised that Tom Carl was going to be in this time slot. And if you were watching the national news, you saw why he couldn't be here. He was on the national news talking about the report that came out, so he had a very good reason. And luckily for us, Tom and I were able to convince Susan Solomon to come here, so certainly this is I still consider this a step up. So we wish Tom could be here, but Susan being here is great. I think you all know Susan. If I were to list all the awards and honors she's attained, I would take the entire 50-minute slot. So just to say that she's well known to all of us, she's internationally renowned. I had to have true confessions with her this morning because, as you know, I was part of Vortex 2. I put 10,100 miles on my rent-a-car. I think my carbon footprint was beyond what should be expected in a 5-week period. So I don't know, this is not good to be introducing Susan and talking about how much mileage I put on my rent-a-car. But anyway, Susan, thank you so much. She's going to be talking today about global climate change assessment, a look backward and forward.
Thank you. It's a great pleasure and an honor to be here. What I'm going to try to do today is to very quickly summarize a little bit about the process of scientific assessment. I'll talk about the 2007 science report of the Intergovernmental Panel on Climate Change, which I was the co-chair for, and tell you a little bit about that process. I'll talk about some new things that have appeared in the literature since then, some of which are related to my own work, and actually one or two items that are covered in that report that Tom Carl's group released yesterday. And I'll also talk a little bit about my own view, and it is just a personal view, of what you may see in the 2013 next major IPCC assessment. I am no longer the co-chair of Working Group 1, so my views are just my own and no one else's. Well, one of the things that I find very inspiring about being involved in the climate change issue is the incredible depth and breadth of coverage of temperature records that we actually have, allowing us to say that indeed virtually the entire world has warmed in the past century. There are a few exceptions, places like this little spot south of Greenland, this little spot in the southeast US, where I think there's more and more evidence now that there are linkages to land use and perhaps biogenic emissions. But apart from those anomalies, we see a very pervasive warming worldwide. It's not confined to urban centers. I don't know of any urban centers out here in the middle of the Atlantic Ocean. And one of the things that I find also very interesting is to have a look at the last 20 warmest years and ask yourself how far back you have to go to find one when you were not alive. Probably for most of us it's down here, number 18. So we are basically living in the warmest period on record. It's about 3/4 of a degree warmer than it was in 1860. That's in Celsius, so it's something like 1.3 degrees Fahrenheit globally average. Well, if you look at the time series of the global average record, it looks something like this, with a gradual warming in the early part of the 20th century, this period of relative cooling in the 60s and 70s. I think there's increasing evidence that that was due to increased sulfate aerosol in the days before we had the Clean Air Acts in this country and before they had much in the way of pollution regulation in Europe. As we cleaned up our act, the global warming signal, I think, clearly has emerged from the record very strongly, and I'll talk more about that in just a couple of minutes. Well, one of the things that you've probably heard a lot about is the question of what's happened in, say, the last 8 or 10 years, and if you go ahead and blow up the individual years, 97 to 2008 looks something like this, and much has been made of that by some people. But interestingly, if you step back and look at, say, 87 to 96, you'll also see similar ups and downs in that record. You step back to 77 to 89, you'll also see ups and downs. So if you looked at any one of these 10 or 11-year periods in isolation, you might reach the conclusion that there'd been no warming, which is obviously wrong. It's quite clear that there has been a very strong warming. So indeed, there are ups and downs from year to year. That's true. Is it relevant to this problem? No. And as I look at some of the types of arguments that one often sees debated in the popular press, they often fall into this category, things that are at face value true, but are not really relevant to the climate problem. And a lot of that has to do with the difficulty people have of distinguishing between weather and climate. That's natural enough because we all experience weather from day to day, so it's a difficult thing for us to integrate in our heads over space and over time, as one must do to look at the climate signal. Well, the concerns about the issue of climate change led to the establishment of the Intergovernmental Panel on Climate Change in 1988. So for more than 20 years, science assessments have been done under the auspices of the IPCC. Its function is to assess published research. It doesn't do research. It doesn't manage research. It assesses what is in the literature. The process takes about 2 years. I'm not going to go into the details of it, but for all of us who publish scientific papers, it is rather interesting to reflect on what it takes to get a scientific paper published in the literature. You write it, you get it reviewed by 2 or 3 colleagues, and then you publish it. Whereas in this case, you write it, you get it reviewed by about 600 expert reviewers worldwide. It's open to anyone to review. You get over 30,000 comments as compared to maybe a couple of dozen on an individual scientific paper. You also get reviews by many dozens of governments. And then the final process is a word-by-word and very, very grueling, if I may say, process of agreeing on the summary with 113 worldwide governments. If you can get 113 governments to agree on something, I think you've got a set of really robust findings that the whole world is willing to take as a basis for discussing other things. So I had the honor of co-chairing that process in 2007. This is Dr. Chin, my colleague, a distinguished glaciologist from China, who was my co-chair, and myself working through the summary for policymakers with those 113 governments. And the way I like to describe the process of assessment is it brings the discipline of science to policy. And that's actually something that the policymakers, I've learned over the years of doing this, the policymakers actually really value that because it gives them a basis in agreed fact that they can then use to discuss things. And they simply don't have that in a lot of the issues they discuss. There are many, many difficult questions that the UN deals with without the benefit of such a basis. So as I'm sitting here doing this, the delegates are arrayed behind their country flags. As you see in any UN process, it's a very formal process. And you can imagine the differences in the views of the various nations and how interesting and challenging it is to talk to them about their viewpoints and get them to agree on science. Well, the type of thing that we were able to get them to agree on in 2007 is illustrated here. It's not just the record of rising atmospheric temperatures that convinces us of global warming. It's also the fact that sea level has been rising, the fact that northern hemisphere snow cover has been declining, glaciers are retreating, Arctic sea ice extent is decreasing, atmospheric water vapor is increasing, and it's increasing in exactly the way one would expect in response to the warming climate. It's not a forcing of the climate, it's a feedback, so it's changing because it's getting hotter, just as the amount of vapor above your tea kettle changes when you make a pot of tea. That enhances the warming, but it's not the cause of the warming. It was the fact that we had so many different measurements by so many independent techniques that led us to think about what kind of language we really wanted to use to describe this. And we really felt that we had to use very unusual and strong and clear language so that the non-expert could understand, as a scientist does, how much more confident one feels when one has several different independent measurements. And so we chose the words warming is unequivocal, and I think that that has been a very helpful way to view this for the world. Well, I've already mentioned the importance of distinguishing between weather and climate. I find it useful when I'm talking to a broad audience to explain to them that fronts are really important. It's the kind of thing they see on the TV weather, so they understand that winter cold fronts can cause large variability locally. You show them a picture like this, and it's easy to explain that it's getting colder here, but probably warmer over there. So there isn't any net loss of heat to the system when a front moves through. It's just moving cold air from one place to another, and that's why averaging over space and or time is critical if you want to look at climate. Well, another way of looking at it is, again, to look at that global temperature record, and these are the changes in January worldwide over the 20th century. If we pick a point up in Canada, we'll see a lot of local variability, but a suggestion of a trend. If we pick a point over here in China, the same kind of thing. Australia, less variability because it's summer down there in January, near Paris, near Denver. If we globally average it, we see how we can beat down the noise and really see a very, very strong and clear signal. You don't have to be a statistician to understand this. So it really helps people to understand, though, that the ups and downs, a warm winter or a cold winter in Denver is not indicative of global warming. One of the things that I will touch on later is the fact that we are seeing fewer cold extremes near Denver nowadays, and that has some implications that have become of great interest in climate. Well, the polar ice caps are a great place to look to understand why this is happening. You can dig up an ice core and look at the record of the Earth's atmosphere over many hundreds of thousands of years. Here's the beginning of a piece of that record for carbon dioxide. If we take a look at the last 10,000 years, it's really interesting to see that the first 9,900 or so of those years, it was rather flat. Some ups and downs, which have been subject to very interesting work and questions about what's causing them, but it's also clear that it's the last 100 years when this enormous rise in carbon dioxide has occurred to the point where today we have about 385 parts per million in our atmosphere, and that's about a third more than we've had in, from this picture, at least 10,000 years. As I'll show you in a minute, it's actually more than we've had in over 600,000 years. So that dramatic increase in the industrial era is the major forcing agent. It's what's forcing the climate to change by changing the energy budget. Well, another thing that sometimes comes up is, well, but what about all those big natural fluxes of carbon? Doesn't the carbon have a cycle? And, you know, doesn't the biosphere emit a lot of carbon? Doesn't the ocean emit a lot of carbon? Of course, it does, if you will, the carbon cycle breathes every year. And that's in response to the northern hemisphere growing cycle. There's also influences that have to do with the uptake in the ocean and in soils. But the human trend is very clear. So are there big natural fluxes? Sure there are. And in fact, you can see them even more clearly if you blow up the last, say, 6 years or so. You see these large swings from season to season. But it's also clear that the overall trend is quite strong and that it's not significantly influenced by these ups and downs. So are the natural fluxes true? Sure they are. Are they relevant? Not to this problem. Here we can go back 600,000 years in the wonderful ice core that's been analyzed by the European group, and you can tack on the last 100 and see how remarkable what we're seeing today is in Earth's history. Last ice age was about 20,000 years ago. The previous warm period, which had carbon levels about the same as what we had before the industrial era, was about 120,000 years ago. Previous ice age, previous warm period. Notice how this thing kind of looks like a clock. It looks like a clock because indeed it is a clock, and it's related to the orbit of the planet around the sun. And I'll show you that in more detail in just a second. Well, this has caused a lot of confusion with people. They say, well, you know, we know about the ice age, climate change has occurred before, why should we worry? Again, it's one of those things that I would say is true and it's not particularly relevant. The ups and downs tell us that something very systematic is going on here, and that's one example of what that thing is. I'm going to go back and show that to you one more time. So the distance between the sun and the earth varies on a very, very slow time scale, many tens of thousands of years. That's what's changing the energy driving the climate system, and that is the fundamental cause of past ice ages. There's also a feedback where as it gets colder, the planet can take up more carbon, particularly in the ocean, and that influences the ups and downs in CO2. which in turn then reinforce the climate change. But the fundamental driver is the orbit. That's not what's happening now. We're heading out of the warm period into another ice age, some people say, but that's not going to start for more than 10,000 years. We understand the orbit well enough to do this, to say that that's the time scale we're talking about. The way that carbon dioxide forcing is increasing today is at a rate that is far, far faster than any change in past ice ages. So these changes confirm that changes in the energy budget, changes in forcing, drive climate change. It's not a reason to say we shouldn't worry. It's actually all the more reason to ask what carbon dioxide forcing is doing to our planet now. It tells us that if we change the forcing, we will see a climate change. Well, what about the sun's brightness? That's not the same as the orbital variations in the energy received. Well, we've seen ups and downs in that. Over the last 30 years, we have excellent records of that, but there are no significant long-term trends that would be responsible for what we're seeing. So is it doing anything to some of the ups and downs? Possibly. Is it driving the long-term trend over the century time scale? No, we don't see any evidence of that in the data. Two different analyses of the calibrations of those particular measurements of the sun. So that is always a challenge in this work, but the one that's believed to be more accurate is the green one, which I believe is based on intercalibration with the space shuttle measurements that were done over time. So the initial calibration, which was probably too high, has been replaced by that one. So there are ups and downs, but no trend. The brightness that's happened here is much smaller than the greenhouse gas forcing. There's been no trend in cosmic rays either, and that's been shown recently. So the solar brightness effect is small. The carbon dioxide effect is the largest. These are the different forcing agents, and I'm not going to have time to go into them in detail, but you can clearly see the dominance of CO2, and the fact that the net is quite strongly positive is clear. So another thing that I'll touch on in just a minute is that carbon dioxide's lifetime in our atmosphere is very long. It lives on average more than 100 years. So every year that we emit carbon is a commitment to climate change for many future generations. Well, another great test, I think, of the fact that when you change the energy budget, you will get a climate response is a major volcanic eruption. We had one in the early 90s. The Pinatubo eruption was predicted to cool the climate, actually, before it was observed. The minute it went off, I believe it was predicted that it would cool by about 0.5 degree globally averaged, and that's quite similar to what actually occurred. Well, this doesn't test all of the feedbacks because it's a short-term response. It doesn't, for example, test the slow feedbacks that might be happening that might involve the vegetation or the ice sheets or the ice shelves. But it does give you a test of things like the degree to which water vapor feedback is probably broadly understood, and the way that clouds are affecting things is also partially tested, at least by such a process, and it gives us confidence that we understand the forcing to climate change response. So are humans responsible for the trend that has happened in the 20th century? There are the observations again. This is what we think would have happened with only natural forcings. You can see the 3 major volcanoes of the last 30 years, which are nicely reflected in the observed record. But you can't easily match what's happened without including the greenhouse gases. In fact, you can't match it at all. So when we include the natural and human effects, it's really nice, I think, that you get those volcanic responses, and you also increasingly see the separation between what the natural forcings would have produced and what actually has occurred. So now I think you'll understand better the progression of the IPCC statements from just saying in the early 90s, when the signal was not as large relative to the noise from year to year as what we see now, that the balance of evidence suggests a discernible human influence has progressively become a stronger and stronger statement. And our statement in 2007 was that most of the global warming in the last 50 years is very likely, that's a 9 out of 10 uncertainty, 9 out of 10 odds, due to human increases in greenhouse gases. I'm going to say a little bit more about why we said that in just a minute. Well, if we take a look at what's going on in the Arctic is very warm. It was also warm in the 1950s to 1940s. At that time, the extent of the warmth wasn't global. Here you see the annual sea ice minimum marching across, and you can see how it's dropped. In 2007, we hit a tremendous record low, which was not predicted. It is an even faster change in sea ice than the models would forecast. 2008 was similar. It was just a little bit higher, and it's going to be very important to see how persistent this is. But at the moment, I think what we can say is that we've seen a clear decrease in Arctic sea ice extent. If we keep warming, it's very likely we'll see more. I want to emphasize that when you change sea ice, that doesn't affect sea level because that ice is already floating. It's the changes in land ice, glaciers and the ice caps and the ice sheets that do affect sea level. Well, why can we say that it's very likely, with 90% odds, that most of the warming is due to increased greenhouse gases? That's not just a number that we pick out of the air. It's based on multiple fingerprints in time and in space. And I just wanted to show you one simple one right here. Here again is the global average. These have now been smoothed over 10 years, so that's why they're a little smoother than some of the previous ones that I showed you. The global land is doing something like this. The global ocean is warming less, and that differential is exactly what we expect to see, excuse me, based on the greenhouse gas increases that have occurred. So this is one example of the many fingerprints that are used. And it's the statistical matching between the models and the measurements that allows us to make this confidence statement. It is based on a rigorous statistical analysis. Well, when I talk to students, one of the things I like to tell them is that they're going to be living in one of the most interesting times to be a climate scientist, because on every continent in the next 50 years, we're going to see a remarkable change, even less than that, actually. We're going to see the signal really emerge strongly from the noise worldwide. So if we take a look at the average temperatures in North America, Europe, et cetera, and we look at what the models predict, how well we match is really, I think, quite amazing. Again, this is another one of those statistical fingerprints that we use. The blue is showing you the, excuse me, the estimated natural variability. If that were to continue into the 21st century, temperatures would probably sit somewhere like that. But what is very likely to happen instead in the next few decades is a remarkable increase in temperature, to the point where things are just going to start booming out of the noise. And as I'll show you in just a minute, one of the interesting questions we have in this area is whether or not the infestation of the pine beetle may be a manifestation of that. But certainly within the next few decades, temperatures worldwide on every continent are going to be dramatically different than they were in the 20th century. And what that's going to do to our ecosystems, to our birds, to our bees, to our water is an area of tremendous interest scientifically. Well, what else is going to happen in a hotter world? As we all know, as the ocean gets hot, it expands. This is well understood physics, and it's the piece of the sea level problem that we can be highly confident about. Another piece that we can be pretty confident about are the contributions from glacier melt. Over 100 glaciers worldwide have been carefully monitored and have been shown to all be decreasing in their extent, with the minor exceptions of some of the ones in Norway, for example, where there's been so much of an increase in precipitation and snowfall. Some of those have increased, but they are by far the exception. Worldwide, glaciers are decreasing. So the future changes just from thermal expansion of the hot ocean and the small glacier melt could be up to 1.5 feet by 2100 and up to 3 feet or a meter within about 2 to 3 centuries. Obviously, those numbers depend on how much greenhouse gas we emit. But what about other processes? What about rapid ice flow? This is something that's really challenging still the glaciological community. When you take a look at pictures like this one from Greenland, they're very dramatic. You literally see rivers of water that some people have argued could carry the that melting water could get all the way to the base of the ice sheet and lubricate the base and allow the ice sheet to literally slip off into the ocean. There's been some recent work suggesting that that process does not operate as quickly as some people had suggested. So there's a lot of questions about whether that mechanism is indeed a significant one. The bottom line, though, is we do see rapid ice loss in some places around the edges of the continent, particularly in Greenland. You can see evidence for ice losses in all these places, especially the Jakobshavn Glacier, which is right there. We see some evidence for increased accumulation on the high central part of the continent, so the issue of what the ice mass balance is averaged over the continent is a tough one. We have short records from the GRACE satellite, which are suggesting ice losses for both Antarctica and Greenland, but they're quite short. It's important to note that we have 7 meters of equivalent sea level on Greenland. So if it were to melt very slowly, say, we would eventually end up with a loss of perhaps most of Greenland, if not all of Greenland. What kind of temperatures would it take to do that, even without rapid ice flow? Well, temperatures warmer than about 2 to 5 degrees Celsius, maintained for many centuries, would melt Greenland. Well, that makes it sort of an inexorable process. It's something that will happen even if they don't happen rapidly. And this is the key question. We know that we are looking at increases at warming levels that should be expected to melt parts of Greenland. How long that will take is really the central question. How important processes like this rapid ice flow that we're seeing really are in the context of the much larger, incredible mass of the ice sheet is a big question. Similarly, there's 5 meters of sea level equivalent in West Antarctica. And that also has been showing signs of rapid ice flow in places like the Pine Island Glacier region. So there's a possibility of loss of parts of Antarctica as well, although East Antarctica, some studies suggest, has been increasing. So basically, the way that I like to describe this is that we see local areas of rapid ice flow. We don't know how applicable that is to the whole ice sheet, either for Greenland or Antarctica. We know that mass balance is important too. If we get more snow in a future wetter world, as we expect, especially for Antarctica, that could offset some of the loss. So the bottom line is an ability to see processes occurring locally that could be important, but an inability to actually quantify their rate and their magnitude in the future. And that's the problem that we're still dealing with. Well, if we had 6 meters of sea level rise, that would massively change the coastline of the United States. All the red areas would be underwater. All these islands as well would be underwater. If we have, and obviously that's a very different Florida, if we have a meter of sea level rise, it would still change Florida quite a bit. And places like Miami, Tampa, Cape Canaveral, a lot of places that I really like would be gone in just a few centuries, and that's just from thermal expansion and small glacier melt. I want to say a little bit about issues of uncertainty. One of the things that I find very interesting is the way the discussion of uncertainty in climate change has evolved. People like to talk about risk and confidence levels these days. And as I've looked back a little bit, and I'm no expert in this, but as I've looked back a little bit, it has struck me that the use of uncertainty and risk language is easy to understand when one talks about structures. You can test the pieces in the laboratory. You have well understood physics that has to do with the safety or the risk associated with such a structure. Similarly, in epidemiology and toxicology, you have lots of samples. You can sample lots of people, and you can get a distribution of the uncertainty and some response to something that you're worried about. And so your ability to provide the kind of statistics that you need is clearly there. Well, clearly we've gotten some spectacular illustrations recently that there are things that we think we understand sometimes that we really don't. And so things like the risk of a stock market collapse, I think, were certainly underestimated by people who studied this. And the question for us is, how do we talk about something like the Greenland ice sheet? How do we talk about climate change in general? And I guess I would say that climate change is a mix of things that we now know quite well, other things that are high impact but highly, highly uncertain risks. And I think we need to, as a community, do more to identify what is well known, so that we don't lose sight of the much more certain pieces of the problem in light of the uncertain risks. Because people won't agree on how much we should worry about safeguarding the Greenland ice sheet. That's a matter of personal values, because different people have different ideas about how much risk is acceptable. What is much more useful is when science is able to inform people about the pieces that it understands and knows well, and I'm afraid we've lost sight of that just a little bit in our field. Well, let me move on and talk about the emission of carbon dioxide. I know this is a little hard to read, but this is a list of the carbon dioxide emissions from fossil fuel burning per capita from a number of the countries that are producing it. The really good news is we are not number one on this slide. That's us here at about 20 tons per person on average in 2006. The Emirates, United Arab Emirates is up here, Qatar and Saudi Arabia is over here. Luxembourg is here. I'll talk more about them in a minute. Australia and Canada typically are near our value, maybe a little higher, a little lower. But basically, we're part of the club of the world's highest emitters, typically somewhere near 20 tons per person per year. In Europe, it's closer to 10. In China, it's more like 5, and I'll come back to that in a minute. And you can see how it decreases as you go down. And one of the things that I've always found disturbing about this plot is that when you just look at it, it's very hard to appreciate what's really going on down in there, and I'm going to show you that in just a second. Well, why do we emit that much carbon? I like to think of it in terms of about a third, a third, a third. About a third is our energy industry, roughly a third is transportation, and roughly a third is everything else. And some of that is industry, some of it is households and the service sector. But in short, doing everything that makes us comfortable, making things that make us richer, going places, all of those things involve the emissions of carbon. Well, now what I'm going to do is turn this around. I'm going to show you the ratio of U.S. emission per person to that of the country of interest. So what I'm showing you here is to try to illuminate how much less emission is really going on per capita in those countries at the bottom of the figure that I showed you previously. And so you can see that for countries like, say, Ethiopia, the per capita emission in Ethiopia is something like 200 times less than ours per year. Places like Kenya is roughly 100 times less. India is about 20. China is roughly 4. So what that's telling you is that as Roger, as he mentioned when he introduced me, drove around in his rental car, he was emitting, I'm sure, more over the course of that work than the average person in Kenya does in a year. When I fly from Colorado to Washington and back, I'm emitting more than a person in Kenya does in a year. And I don't want to say how many times a year I actually do that. So it's really quite sobering to think about this, because the numbers that are also, and I guess it's easy perhaps to understand that a person living like this is emitting a lot less carbon than one living like this or living like that. And if you were wondering why Luxembourg's emissions are higher than ours, a big part of that is because they're very wealthy and they fly a lot. But if you go ahead and integrate across the developing world, the people in the developing world today, of which there are about 5.5 billion of them, emit about 5 times less fossil carbon per person than the 1 billion people in the developed world. That's a pretty sobering number, because what it tells you is that if, in the course of their development, these 5.5 billion people begin to live like us, the carbon emissions worldwide are going to shoot up in an incredible way, and the planet is going to get very hot. It would correspond to about 1,000 parts per million of CO2 by the end of the century, and temperatures some 10 degrees Fahrenheit on average, warmer than they are today. So that's the crux of the issue. If you take a look at the last decade, much has been made of the fact that China and U.S. emissions are now about the same. It's very, very similar actually now. In the old days, they were emitting much less than we were, but of course it's very interesting to go ahead and do it again per person, not just integrated across the country. So as I mentioned, on a per capita basis, we emit about 20 tons per person, they emit about 5. So they're still emitting 4 times less than we are, even though their total integrated value is the same, and that's because they have about 4 times as many people. And don't congratulate yourself too much on the fact that our emissions seem to have dropped slightly in the last decade. That's actually mainly due to immigration and increased population. It's not due to getting more efficient. So to make this problem even worse, we have to also think about how far we've pushed the carbon cycle out of balance. And I find the analogy with bathtubs to be a really helpful way to think about this. We know that stabilization of CO2 would require about 50% less emission for a few decades, and then about 80% less emission. So unlike many other pollution problems, such as smog or ozone, acid rain, that kind of stuff, and when I say ozone, I mean tropospheric ozone, not stratospheric ozone. It's not the case that if we stabilized emissions, the climate change would stabilize. We actually have to cut emission in order to stabilize the system. And most people don't understand why that is, but the reason, of course, is illustrated here. The amount of carbon in the atmosphere is kind of like the water in a bathtub. The drain is the sink to things like the ocean and the biosphere and the soils. And the source is us. And basically, we've pushed the system way out of balance. We're putting in much more carbon than the drain can take away. So the water in the bathtub is slowly rising. Just keeping the amount coming in the same won't stop the bathtub from having its level rise, because the amount coming in is so much bigger than the amount going out. So in order to stabilize it, we would have to do something like this. And the real issue is that 5/6 of the people on the planet are now emitting 5 times less per person than the other 1/6. So if they start emitting like us, that's what we're looking at, and that's a real problem. So in addition to the number of people and the imbalance there, we also have this already existing carbon imbalance, which even if we kept everything the same, would make our climate get a lot hotter. What can we do about it? Well, maybe some kind of engineering, cool the planet with little mirrors out in space, or use real or artificial trees to soak up the carbon. I'm not going to talk about that here. I'm not saying we shouldn't do it. I'm just saying we better be very sure of what we're doing if we decide to do it. I'm running out of time, and I do want to leave a bit of time for questions, so I'm going to very quickly go through the rest of it. If we take a look at temperatures in the summer in Switzerland, we see a distribution that looks something like this. 1947 was the previous hottest summer before that incredibly hot European summer of 2003. This, I think, is a great illustration of how important it is to understand variability in temperature. If we have a distribution of Swiss temperatures that looks something like this, the 1 in 40-year unusually hot summer might be something like this. If we shift that distribution over by, say, 1 standard deviation, which would only be a few degrees of warming, that would make that 1 in 40-year event into a 1 in 6-year event. So we would see a much larger frequency of hot extremes. Basically, it's simple calculus, and what it's telling you is that a shift in the distribution of temperatures will have a very large relative effect on the slopes of this distribution than it does near the mean. By the middle of the century, Europe is likely to have many more summers like 2003, perhaps 1 in every 2. Well, I promised you I would talk a little bit about the pine beetle. If you've been over on the western slope lately, it's really quite disturbing, and it's also quite pervasive in parts of Canada where the land is completely unmanaged. What we're seeing is a massive die-off of particularly the lodgepole pine trees. So this isn't fall color. These are dead pine trees, and It's really very sad to see them. Why are they dying? Well, there are several factors. Reduced moisture, the trees are stressed. As the world has gotten hotter, there's a longer beetle breeding season, so they have more time between the last frost in the beginning of the summer and the first frost in the beginning, the last frost at the end of the winter and the first frost in the beginning of the next winter. That allows them to get in 2 cycles of breeding rather than 1. And if you kind of think about what would happen to the human population, if suddenly instead of it taking 9 months to make a baby, it only takes 4.5, you can get a sense of why 2 cycles is really going to mean a lot of explosion of population. The other thing that's been cited is fewer extreme cold snaps to kill the beetles in winter. When it gets below about minus 20 degrees Fahrenheit, they die, and we're not seeing that nearly as often in the winter anymore. So the question that is unanswered, and there's a lot of work going on to try to address it, is whether this unusual die-off of the trees is due to climate change. It is unprecedented in terms of its extent in British Columbia. It has happened before, but not to this extent. Well, I'm really running out of time now. Let me try to talk a little bit about rainfall, and I'm just going to touch on it, and I'm going to skip a bunch of stuff at the end here. One of the things that was new in the 4th assessment report was the much more extensive discussion of changes in not just temperature, but also in other things, and particularly rainfall than what we had had before. And this figure is really quite striking. The stippled areas show where 90% of the models agree on the nature of the change. So what you're seeing here is that in the regions with orange, what that's telling you is that we predict that by the end of the 21st century, for a medium emission scenario, you expect to see something like a 10 to 20% decrease in rainfall in December, January, February is what this example is. So 20% less rain is an enormous change in rainfall for this area. Similarly, the Mediterranean is such an area. The places that are colored but not stippled, 2/3 of the models agree. The places that are white is where the models, fewer than 2/3 of the models agree on the sign of the effect. So a big chunk of the U.S., we don't know what's going to happen, but in the northern U.S., we predict more rainfall. In the southern U.S., less. And parts of Australia, we have that situation. Again, the Mediterranean is one of the places with the most robust change. The bottom line is that it's at high latitudes we expect things to get wetter in both hemispheres, but at mid to low latitudes we expect the dry to get drier and the wet to get wetter. So the dry southwest is probably going to get drier and the wet northwest is probably going to get wetter. These are huge changes. In the Dust Bowl era in the U.S., we had about 10% less rain for about 10 to 15 years, and other major droughts in the world have been of that order as well. Here we're talking about changes worldwide, all these places at the same time, with massive changes in rainfall comparable to the American Dust Bowl. I'm not going to have much time to talk about the details of this. This is just showing it to you in a slightly different format. This is the changes uniquely in the dry seasons, which is when the biggest effects occur. And they're of the order of the same kind of numbers, something like 5 to 15% per degree of global warming. So it's a tremendous change in the dry seasons. And the dry seasons, as I say, are when you expect to see the biggest effect. This is just showing you the consistency across the various models in those various regions. The agreement on moistening at high latitudes is very strong. Similarly, if you look at Southern Europe, the agreement is quite strong and to my eye, very, very disturbing. So what are we talking about? Well, if we go to 1,000 parts per million of carbon dioxide by the end of this century, we would be looking at drying of Southern Europe and Northern Africa in their dry seasons on the order of 30%, which is an incredible change. So places like Italy and Greece would literally become like the Sahara in that case. Southwest North America, it's about 20%. If we go to other levels of CO2, you can take a look at what that means for whatever level you're interested in. Let's take 450 just as an example. It's something close to 10% for Southern Europe and Northern Africa. So the other thing that was highlighted in terms of rainfall yesterday in the Climate Change Science Program report, and I really urge you to go on the web and take a look at that really quite excellent report, is that we are seeing when it rains harder, and we're seeing that across much of the United States. So the reason that's happening is that we have more moisture in a hotter atmosphere. When it does rain, it's going to pour more often. It doesn't mean you get necessarily more total rain, but you get more heavy rainfall. So this is the kind of trend that we've seen in North America, and these are the forecasts out to the future, depending on how much carbon we emit. So we're looking at a different world in our Arctic. We're looking at more intense and longer heat waves and droughts, more fires, more ecosystem change, and more rain in some places, but less in others, and more heavy rain for everybody. Okay, I'm not going to talk about choices and what we could do. It is interesting to me that there are many signs of the great degree of interest in this problem, which has pervaded not only people, but also industry. We're seeing lots of people thinking about this problem differently. Well, some of the things that I hope you remember are indicated here. I'm not going to go through all of them. This is one of the interesting ones. Young people today are going to live in a world some 5 to 10 degrees Fahrenheit warmer by the time they're old men and women if we keep continuing to ramp up our emissions. Rainfall changes, I talked a lot about them. To me, they are one of the biggest issues in climate change today. The question of extremes is very substantial as well. Those young people will be living in situations of heat waves that will be they'll be even worse than the worst that you've seen today. So clearly it challenges us not only to think beyond our own backyards, but also beyond our own generation. IPCC was an incredible experience for me. Why was it so successful? Well, we've worked very hard, I think, to not only advance the climate science in our community, but through IPCC, we've been able to make the presentation of those results clearer and clearer, and we've disseminated the information quite carefully. As you know, the Nobel Peace Prize for 2007 was awarded to the IPCC and Al Gore Jr., and the citation, I think, was very interesting. It was the first time the Peace Prize was given for greater knowledge. And I found that a very significant thing, recognizing as it does that science has something to contribute to world peace. The achievement here rests with IPCC's authors. I had a fantastic author team of over 150 people from all around the world working with me on the report. And I also want to acknowledge the very helpful contributions by all of the reviewers to the process. So if I look at the next report, the kinds of things that I expect to see in it are indicated here. I think you're going to see a lot more discussion of things like soot, particularly what does soot do to the Arctic, to the issue of Arctic sea ice? What does it do to circulation? What does it and other aerosols do to circulation and precipitation changes? As I emphasized quite a bit, we're going beyond global warming and talking about human influences in other parts of the climate system, including drought, Arctic sea ice, wind patterns. You can kind of think of this no longer as just a climate change report, but really an Earth system report. And I think you're going to see more of that in the future. You're going to see more discussion of how much we're committed to having more warming and how much we can make choices about emissions in the long term and in the near term to influence those commitments. I think you'll see a more integrated approach to scenarios, which will include things like land use. Obviously, the sea level rise issue will have to be addressed with whatever information is available. There's a meeting taking place in just a few weeks in Venice to plan the fifth assessment report outline, and I'm sure you'll be hearing about that from our colleagues who are there. And thank you very much for your attention.
Questions? We have a few minutes for questions. A lot of thought-provoking stuff in there. Oh, Steve. Yeah, please use the microphone.
Nelson, NSF. Susan, as science is trying to help inform policy decisions, it seems like it is not a question now of if, but how much and maybe how fast. Where do you think the science should be putting its efforts right now? You know, what are the critical policy issues that are maybe still a bit unclear that we could contribute to?
Well, I kind of tried to touch on that here. I think you're going to see a lot of discussion of the extent to which mitigation on carbon dioxide versus mitigation of, say, methane or soot might influence the Arctic, for example. So I think you're going to see a lot of discussion on the range of aerosols and gases that contribute to climate change and what sorts of choices can be made regarding those. You'll also see a lot more discussion, I think, not just on the temperature changes, but also on the other parts of the climate system, as I mentioned. From the impacts point of view, you'll certainly see a lot of discussion on issues like the pine beetle. To what extent do we understand that? And I guess I would say that every region has its pine beetle. You know, the pine beetle happens to be our issue here in Colorado that to me is sort of the poster child issue. For other places, it's sea level rise or changes in parts of their ecosystems. Bird migrations are a big one, something that the Audubon Society has been very involved in. Question of extinction, how well do we understand which species will go extinct? You'll see a lot more discussion of that kind of thing. That's about the most we can do for the policy people, in my opinion. At some point, they're going to be asking questions about economics and the extent to which we understand the cost of the damages versus the cost of mitigation. That's the kind of thing that Working Group 3 of the IPCC deals with, but you know, I think that's one of those areas of very high uncertainty, which I don't want to really spend a lot of time on now. Do we have another question?
Sue.
Hi, Susan. Thanks for a fabulous talk. So this is a NSF Facilities Users Workshop. So we've been talking a lot about observational needs from various aspects of the science. So my question to you is, what do you see as some of the major observational needs in the context of advancing understanding around how science is changing that's going to impact climate?
Yeah, it's a hard one in this context because obviously an organization like this one focuses less on long-term monitoring, perhaps, and more on issues of process studies. But I don't think that should be daunting to you. The reason I put this slide up, as I was putting it up, I was thinking about all the ways in which the sorts of things that I know of that are done within the facilities here do contribute to these issues. And certainly process studies on understanding the role of the different aerosols and gases in the climate system, to what extent, for example, the reflectivity of snow is influenced by soot, or rainfall is influenced by emissions that have to do with aerosols, both organics and sulfate. You know, those are all the kinds of issues that first need to be understood from a process point of view before you can talk about doing the kind of monitoring that would help you to figure out how they're changing over time. So I see a lot of opportunities up in here. Obviously, I'm a chemist, so those are the ones I'm thinking about. But if I were the man standing behind me, I would probably say, well, but you know, we need to do process studies to understand whether tornadoes are changing or whether they could change in the future. And that's kind of part of this second issue here. I think circulation changes. The drivers of circulation patterns are another type of issue where this institution has a lot of capability. So I think the main focus that I would just, you know, and it's an obvious one, is on the understanding of the key processes embedded in these first two items is probably the area of the greatest potential here. Yes.
Yes, Jacob Fugel from EOL. We talked about in this workshop about going more globally instead of focusing on just what we measure here and kind of northern mid-latitudes where there's more wealthy nations, a lot of people, more science is done there. How about the areas that are not as well observed, either over the ocean or Africa or some places like that? How important are those measurements to further progress in knowing what climate change is going to do this century?
Yeah, I mean, obviously, investigations worldwide are necessary to understand global climate change. And the ability of the U.S. to help the whole world to understand questions like the extent to which climate change may be more pressing, say, for Africa than for other places is always a question. One of the things I'll just point out, which I do find kind of interesting, if this thing will let me, is if you take a look at this one, it does provide you with some ideas about where you might go in the near term and expect to see some of the biggest signals. Now, admittedly, you can ask yourself how certain are some of these things, but take a look at South America, for example. Very, very interesting that the variability in South America is less than, say, North America. Well, that's maybe not too surprising. It's surrounded by a lot of ocean, so it's a much more maritime climate. So, you certainly expect to see the biggest signals coming out in South America relative to the noise in the near term compared to, say, North America. Maybe that's an opportunity that deserves some thought. I don't know. A lot of questions have been raised about the influence of the aerosol indirect effect in affecting places like South America because of biomass burning. So, there's opportunities for understanding pieces of the problem that are critical worldwide. And I can't really tell you there's a particular hotspot, but I kind of do find that sort of intriguing. Is that even true? It would be really nice to go through variable by variable, not just for temperature, but for other things.
Okay, Steve, maybe this last question.
Steve Onkley from EOL. Just continuing the theme of how observations could help, are there any particular weaknesses in the model parameterizations or physics that you think a targeted set of observations would help?
Well, I mean, you don't need me to give you the usual statement on that, do you really? I guess you can always talk about clouds being the key uncertainty still, which of course it is. But I guess maybe to be more specific, I do think that the issue of the aerosol coupling to clouds, not only for temperature, but also for rainfall, is by far one of the biggest major uncertainties facing us today in this issue. So I would call the aerosol-cloud interaction as one of the top ones on my personal list. And people don't really realize how much of the climate change has been offset by aerosols to date. It's been really quite amazing. Jim Hansen likes to talk about that as a Faustian bargain. We're emitting aerosols so that we can offset some of our carbon, but in the end, the second that we stop emitting aerosols or the aerosol precursors, we will see a rapid change in climate. So understanding that in more detail, I think, becomes more pressing now that we see, for example, the increased emission from China. There can be little doubt that the increased CO2 emission from China, which I showed you, must be associated also with an increased emission of all kinds of aerosol precursors and aerosols. What is that doing to our climate system is an incredibly important problem and not one that's well understood at all. So
let's thank Susan for a very stimulating presentation. Are you going to be around during our break, which is at 9:45?